Hi everyone, Mr. C here. So today we're going to do a crash course on electron configuration, orbital diagrams, and how to draw a Bohr model. And then we'll finish off with periodic trends. So just a reminder, electron configuration uses this periodic table graph here. So we have four parts to the periodic table: the S block, P block, D block, and F block. And basically the way you do configuration, you always read it like a book, so we're going from left to right and then down the page. And we're going to locate our atom, and then we're going to write down the correct configuration for where that atom is. So we have cobalt 60. What that means is we're going to look at where cobalt 60 is, and that's going to be somewhere in the D block. Specifically, we are right here. So 1, 2, 3, 4, 5, 6. Cobalt 60 is right here in the 3D block. So to do configuration for that, we're going to start with the 1s column and work our way down. So we have 1s2 to start. Every single time you do configuration, you're always going to start with 1s2. And the way that looks for orbital diagram will be a line with 2 electrons. We're only going to do the orbital diagram for the last electrons. Over here in the Bohr model, we're going to put 2 electrons in my first ring, because 1 means that it's the first ring, S means a shape, and S has nothing to do with the Bohr model. It just has to do with how the electrons pair up. The 2 here has to do with 2 electrons. So the exponent is the number of electrons. The number that comes out front is which ring you're on. So real quick, after 1s2, we're done with the first ring. So you can only have 2 electrons on your first ring. Moving on, after 1s2, we should have, continuing on, 2s2. So when I do this, I'm going to be 2s2. And when I go back to the table here, that's my next column. So that's 2s2. What that means is my second ring gets 2 more electrons. So I'm going to pair them up. 1, 2. Okay, so after 2s2, we look here, it's 2p6. So 2p6 is next. And I'm going to continue this a little bit faster so that we get the configuration. So 2s2. Then we have 2p6 because it's full. And when I do my ring, I'm just going to keep adding electrons. So I add 6 electrons in my second ring. First, you spread them out. 1, 2, 3. Then you pair them up. 4, 5, 6. So far, once you have it all the way up to 2p6, you have 2 full rings here. After 2p6, we got to go through the 3s column. So this is 3s2, this is 3p6, and that adds 8 more electrons. 2 from the s, 6 from the p. So when I do this out, I'm actually going to get 3s2 and then 3p6. Like that. So when I put the electrons on, I get 8 more. So this is the 3s2, and the 3p6 goes 1, 2, 3 before pairing up, 4, 5, 6. Doesn't really matter which ones you pair up first. As long as you spread them out first, you're good to go. Okay, now cobalt is here in the D block, so we're almost there. We have to go through 4s2, and then 3d, 1, 2, 3, 4, 5, 6. So that's 3d6. So when we're here, we're going to go back into the configuration and finish it off. So we get 4s2, 3d6. So that's your full final configuration for cobalt. Now the hard part is actually putting the electrons on the ring here. So when you put the electrons on the ring, you have to put the 4s2 electrons first. So that's going to go on the 4th ring. Pair them up. And then for 3d6, the 3 out front means that I'm going to go on my 3rd ring. And regarding which ones to pair up, we're going to have to do the orbital diagram to figure that one out. So before I finish the Bohr model, let's look at just my last couple for the orbital diagram. So I have 4s2. S orbitals have one line, one orbital. So 4s is full. There's 2 electrons. They're pairing up. They're having a nice day. So that's my pair there, 4s2. Now for the Ds. Ds can have up to 10 electrons, which means 5 orbitals. Because each line or each orbital can have 2 electrons, I have 5 lines times 2 electrons can give me up to 10. Now the 3d orbitals are higher in energy than the 4s, and that's why they get filled later. So once you put these 2 into the 4th ring, you're going to go back to the 3rd ring and put in 6. Now they spread out, so 1, 2, 3, 4, 5. They spread out before pairing up to get your 6th. So that's the 6th one. So what we need is 5 electrons that look like this in the 3rd ring. We're going to go 1, 2, 3, 4, and 5. Now these don't have to be perfect. As long as you spread them out, you're good. And then you have 1 pair, so you're just going to pick 1 to pair up. So make that your 6th one. And that is the electron configuration and the way they look for cobalt. Now cobalt is CO, so I'll just write CO for the symbol. Cobalt has 27 protons. And because it's neutral, it should also have 27 electrons. So if you're ever confused on how many electrons you have, it should equal the number of protons if you are neutral. There are, in fact, 27 electrons in here. Now for neutrons, 27 plus what gives you your mass number of 60 up here. So 30 plus 30 is 60, which means 27 plus 33 neutrons gives you cobalt 60. So that's your recap of configuration. Hey everyone, Mr. C again here to do periodic trends. We are going to start with Coulomb's law. So Coulomb's law just tells you that like charges repel, opposite charges attract. And the other thing Coulomb's law tells you that's very important is as the distance between 2 charged particles decreases, as they get closer together, your electrical force or electrical attraction is going to increase. So as this denominator gets smaller, as your distance gets smaller, the electrical force actually increases. So that's just using the math there. So as distance decreases, as the electrons here get closer to the nucleus of the atom, it's going to be harder to remove it. And that's what's behind all of these trends. So a couple of recaps here. The easiest trend to know is that your metals are to the bottom left and your nonmetals are to the top right. With the exception of hydrogen, group 1, group 2, all your transition metals, and group 3, most of group 3, not boron. But you have a lot of metals down here. Okay, so to review the radius trend, the radius of an atom is just the distance from the nucleus to the outer electron. So as a reminder here, as you go down the periodic table, you're going to add a ring each time. So the first row has 1 ring, the second row has 2 rings. So clearly, that's going to be a bigger atom. And if you think about it, these outer electrons in the second ring, they can't get that close to the nucleus because these first 2 electrons in my first ring are blocking them. So as you increase the number of rings, you get more electrons that are blocking the axis. So once you get up to like 7 rings, those electrons all the way out on the 7th ring, they're not being pulled very much into the nucleus. That's why the atom is so big. Now, going left to right here is very interesting because I keep the fact that I have 2 rings true for this second row. So the ring number doesn't change. But what does change is the number of protons. So this is lithium right here where I'm starring. This is atom number 3. That means I have 3 protons. Beryllium, I have 4. boron I have 5, and all the way over here, neon I have 10 protons. So 3 protons versus 10 protons, if I still have 2 rings, 10 protons is going to be pulling me in a lot more than 3 protons. So because I have all 10 protons over here, that's a stronger kind of like magnet. So the electrons on the second ring are going to be way closer to this stronger nucleus. So hopefully that makes sense. The bigger your nucleus is, the closer that the electrons are going to be pulled into it, and the smaller the atom gets. So the trend here, bottom left is where the big ones are. Okay, moving on to ionization energy. Basically, it's the energy required to remove an electron. And this also has to do with size, but going the other way. So this trend is actually going to go up and to the right. And it includes, there are a couple of exceptions, but for the general trend, we're going to go up and to the right here. The way you can explain this one is as the atom gets bigger, so as you get more and more and more rings, the electrons get further away from the center of the nucleus. And if your electron is hanging way out here, it's a lot easier to remove it than it is if you only have like 2 rings. These guys are really close to the center, so it's going to be a lot harder. It's going to require a lot more energy to remove this one than it is this one. So as atoms get bigger, as you go down the periodic table, your ionization energy goes down. And then going left to right, same thing. So as you go left to right here, your size is shrinking. And when your size shrinks, it's harder to take that electron. So when it's harder to take that electron, your ionization energy increases. So size goes down, ionization energy goes up. So that's that trend. Just a quick crash course here. Electronegativity is basically how good you are at attracting electrons, aka electron riz. If you have a big electronegativity, you want electrons. Now, everybody wants electrons, but the ones that are high with electronegativity really want electrons. So you're not necessarily bad at attracting them, but you're worse than the other ones. So going over here, as you go up and to the right, again, you get higher electronegativities, with the exception of the noble gases, because noble gases don't want an electron. Remember, electronegativity is the ability to attract electrons. These guys don't want another electron. Now, xenon can sort of bond and do things, so don't worry too much about these. But helium, neon, and argon definitely cannot. So these noble gases here do not participate in this trend. The highest electronegativity is our big bully, fluorine. And fluorine, if you think about it, fluorine has all 7 valence electrons. We're almost at 8. You want to get 8, and you have 7. That's really, really, really close. So that atom is going to basically beg for an electron. And because fluorine is the smallest one in group 7, it's going to be better at attracting those electrons. If you're like down here at iodine, like, yes, you have 7 valence electrons, but you're bigger, so that nucleus can't really reach outside electrons as well. So fluorine is going to automatically be best. Now, let's say you're over here at like lithium, right? So we just explained why going up and down makes it like easier or harder to attract electrons. But now let's talk left to right. So lithium only has 1 valence electron, right? And that also kind of makes it large. Lithium is larger than fluorine, so it is harder to attract an electron because of that. But there's more to it, right? So fluorine has 7 out of 8 valence electrons. Lithium only has 1 out of 8. So if it attracts another electron, okay, now you have 2 valence. That's okay, but it's not all 8. So these guys aren't as electronegative, because getting an electron isn't as rewarding for the atom as it is for, say, fluorine. So that's just the general introduction to electronegativity. Just remember, fluorine's your bully, and the ones down here like cesium, francium, these guys do not have a very good electronegativity. And one more time, noble gases do not participate in this trend. Okay. So moving on to reactivity. Reactivity, there are two places on the table for it. There's the bottom left and there's the top right. Basically, reactivity has to do with moving electrons. And if your electrons are either easy to leave or easily attracted to the atom, you get a movement of electrons which causes reactions. So for example, let's talk about francium way at the bottom here, right? Francium's huge. Think about like a gigantic atom, right? Your electron, you only have one valence electron. That's it. It's going to be super, super easy to take that electron away. Low ionization energy, easy to take that electron, very reactive. At the top right, disregarding the noble gases again, over here we have fluorine, which is super electronegative. So if your atom is very electronegative, it's going to be easy to attract electrons. And if you attract electrons into your atom, so if the electron goes this way, you're still moving an electron. That causes electron motion because it's attracting an electron. So therefore, you're going to be reactive. So either if you're easily able to lose an electron or your atom is very easily able to gain one, you're going to be reactive. These are the two most reactive elements. Elements that are around this area are usually pretty reactive with most things, with some exceptions. The middle guys, like your D block elements, they're not as reactive. And that's why gold and silver, they don't react with much. Here is your periodic table that just summarizes everything. So here you go. As you can see, bottom left and top right, except for the nobles, are very, very reactive. As you go to the right, ionization energy and electronegativity increase. Now again, electronegativity only increases until fluorine. And then when you go down and to the left, your radius will increase. So I hope this image helps you a lot. Good luck tomorrow. And I have some summaries here. If you want to pause the video and read this, you can. But yeah, hopefully that helped. Peace.